Right, I'm going to take you on a datasheet walkthrough. So you're going to see all the equations that are available in component 1 and component 2. So this is the first part of the datasheet. You've got all the preferred resistor values there. Obviously you've got the decade multiples or sub-multiples. So for example, on the end there you've got 91, it could be 9.1, it could be 910, etc, etc. One thing to point out when they say select a preferred value from the E24 series, if you're using or you're working the resistor out for an LED requires a maximum current. So if you've got a maximum current, then you go for the resistor value below. Okay, and then if you've got something like a Zener diode question, the Zener diode requires a minimum current. So if you need a minimum current, then you're going to go for the resistor below. So before when I said about maximum current, it's a one above. So for example, if you've got a value and you've worked it out to be something like 31 ohms. If it is for a resistor, you'll go for 33 because you want to limit the current. If you worked out to be 31 ohms and it's for a Zener diode, you'd go for 30 because you would need a minimum current. Okay, I hope that makes sense. On to the next bit. These prefixes are in pretty much every calculation, so you really need to do that. I mean, you really can't be now, if you see something like working out a breakpoint, if you see 22 nanofarads, just put in 22 in. Yeah, so they're there for a reason. So, you know, nano, for example, times 10 to the minus 9. Your calculator has a times 10 to the power of button. That's on your calculator. Then you just put minus 9 in. Okay. Rule of thumb, if you're using Ohm's law, so V equals IR, and quite often with Ohm's law we work in normal volts, 1, 2, 3, 4, 5, etc. We work in milliamps, so therefore the answers are usually in kilo ohms. Doesn't say all the time that happens, but if you had something like, I don't know, let's go for 10 volts and 2 milliamps, then I can go R equals V over I. So I can literally, in my calculator, just go 10 over 2. I'm not going to put 2 times 10 to the minus 3, because I know that if I've used milli there, it comes out in kilo ohms. So you can do that. Yeah, milli and kilo. So nice little rule of thumb, but generally speaking, please use the prefixes. They are there for a reason. When we look at things like wireless comms, we look at big values, mega, giga, things like that, because you're talking about frequencies and things like that. Okay, so that the whole scope of these prefixes is used. Okay, this is core concepts. So you can see with this, there's not a lot that they give you on core concepts. In fact, to be absolutely honest with you, we rarely use these equations anyway, but I'll explain what they are. This first one here, the capacitance is the charge over the voltage. So capacitor value measured in farads is charge over voltage. Hopefully, you know, it won't come up if it does. Right, these two are very interesting. They're the same equation. They're for measuring capacitors in series. So to measure capacitors in series, if you think about it, the overall capacitance will reduce if you add another capacitor in series. Yeah. And to measure capacitors in parallel, so that's series. To measure capacitors in parallel, if you think about it, the overall capacitance would increase because you've got an extra size plate. So that'll be in parallel. So the good thing about these equations is, for resistors, it's the opposite. So this would be, these would be R in parallel. Yeah. Okay, so it's good because if you get, oh, how do you work these resistors out in parallel? You don't need to remember the equation. The bottom one there only works for two resistors. can't do it for 3, but for 2 resistors you can use the bottom one. If it's 3, you have to go for the top one, the 1/1. Okay. Right, what else is in core concepts? Well, it's the most important one because maybe about half your paper is using core concepts. Well, you've got bog standard Ohm's law. Yeah, that, as you know, that comes up everywhere. You can't get away from that one. Okay, we have power is V times I. You need to remember those. They're not on the data sheet, as you can see. Obviously, you've got different derivations of power. You could also do I squared R, but it's ones you'd have to remember. V squared over R. So you could also use those, but V times I is an easy one to remember. Okay, and then obviously I times R for your voltage. Okay, obviously we've got the circuit rules. Voltage and current. So obviously just remember this one really, if it's straightforward. There we go. Okay. So obviously just think about it logically, if you're in series, then you're going to get volt drops around the circuit which will add up to the supply. So they're shared amongst the components. Doesn't have to be equal share, as I'll show you with a potential divider. And the current obviously stays the same. Yeah. And then obviously it's the opposite. So in parallel, the voltage is the same and the current splits at a junction. Okay, and then obviously potential divider. Let's see if I can draw it like this instead. Here we go. Here's my this is my table. Here's my basket on the table. Okay, so we've got 3 apples there, 2 apples on the side. So how many apples are on the side? We'll say apples on side equals 2 lots of the total. 2/5 of the apple are on the side. That's ratios. A lot of this paper is on ratios, yeah? So if you could see the same thing with this, if you've got something like 10 volts, 0 volts, 2K and 3K, V equals 2/5 of 10 volts, which would be 4 volts. Okay, this is core concepts. It is everywhere. Series parallel circuit rules, Ohm's law, power, potential dividers. Okay, can't stress how important it is just to get this in your brain. But yeah, as I say, it's not on the data. All the red stuff I've written there, it's not on the data sheet, is it? Okay. So, semiconductors. So you have transistors and you have MOSFETs. For transistors, there's a simple equation there, and it is essentially that the input current, which is called the base current, if you multiply that by the gain, which we call HFE, it's the gain of the transistor, so input current times gain equals output current, which is the current that goes into the collector. It's as simple as that. This is pretty much the same equation here. The only difference is with a MOSFET, it's the voltage that controls the output current. So input voltage times your amplification, your gain. We call it transconductance for MOSFET. So input times your amplification equals your output current, which you call the drain current. Okay, and you can also work out the power in a MOSFET. If you know the drain current and you know the resistance between the drain and the source when it's on, that's basically the resistance of the MOSFET. You may have seen from the previous slide, power is I squared R, so that's where that equation comes from. So let me just get my pen, just to remind you. I'll just sketch this over here, shall I? Sketch this over here. So you'd probably have something that looks like that for the transistor switching circuit. It might have a bulb there or something, some sort of power supply there, and then some sort of 0 volt rail there. Okay, other things they can ask you about this, obviously, yeah, so a collector, emitter and base. Other things they can ask you about this is work out the voltage across that top resistor to find a collector current. That's Ohm's law. They could ask you to work out the voltage there. That's core concept, should I say, or Ohm's law. Yeah. They could tell you to do a potential divider here. That's potential divider. It's all core concepts. They could say that's a variable resistor, thermistor. They could say that's a variable resistor. What's going to happen? They could ask you to plot a graph where you've got off, active, saturated. Do you remember that one? Off, active, saturated. Other things they could ask you. But in terms of any other equation, apart from that first one that I've said, apart from that one, it's circuit rules, isn't it? It's Ohm's law and potential dividers. Similarly, exactly the same with this. They can ask you to work out, there you go, do you remember what it looks like? It looks like that. Okay, so it looks something like that, but exactly the same. Switching circuit, they can ask you to find out the same sorts of things with this one. Okay, Year 2 power supplies, there's no equations, but you do need to know what's inside the MOSFET and also what's inside the transistor, the NPN bit. So I'd reread the notes on that, which are found on SharePoint. But in terms of the actual equations, when you see semiconductors, don't be scared. There's 3 equations. Well, you might be thinking, well, there's not 3. There's more. Well, obviously, core concepts runs through the whole thing. So look at those 3 equations and look at core concepts. You will 100% be able to get all of the marks just from doing those. Okay, logic systems. The only 2 equations they give you are 2 Boolean identities. Okay, so you will likely use those Boolean identities with De Morgan's theorem. Split the line, change the sign. That's De Morgan. Split the line, change the sign. Okay. Other things about logic systems. You need to know your 7 basic logic gates. You really do need to know them by now. Yeah, you need to know what they are. I'm not going to draw them all. You need to know your 7 basic logic gates. You need to know your NAND gate conversions. Yeah. So how do I take a NAND gate? God, that's badly drawn. Put them together to make other logic gates. For example, that would be an OR gate. Yeah. You need to know how to do Carnot maps. Remember grouping 1s, 2s, 4s, or 8s. Hopefully straightforward. But yeah, logic system is what I call the bread and butter, really. But even core concepts does come up in that, because sometimes they might give you 5 volt and 0 volt round, and they might say something like that. They might say, what's the logic level when switch A is pressed, for example. Well, you need to know, therefore, if it's pressed, what's happening with the current. You need to know when I press that switch, a logic 1 happens, so it'll be 1 when pressed, won't it? So you still need to understand what's going on. They might even give you an LED and a resistor, and then ask you to work out the resistor value. You're using core concepts, you're using Ohm's law. It's all going back to that, isn't it? Okay. Okay, so this is op amps. You can see there's a lot of equations. Gain is V out over V in. That's a bog standard straightforward one. So they might give you a graph and ask you to plot the output voltage if they've given you the input voltage, usually a sine wave. Be careful in case it clips, so look at the saturation voltage. These 2, this is obviously a non-inverting, this is an inverting. I'm sure you guys all know now. Resistors don't go to the plus sign, do they? Yeah, so you know how to draw those now, don't you? If it's non-inverting there, then obviously that would be V in, that would be 0 volts, just so you know, that would be a non-inverting one there. Okay, I'm not going to draw the other one. This equation here is a summing amp or a mixer. Okay, that one can come up as well on audio, because obviously you can get mixers in that, and it can also come up in ADCs, DACs, because you can use it for a DAC, can't you? It's the same sort of thing. Yeah. Again, there's no such thing as a non-inverting mixer, you can't get non-inverting, so the resistors will always go to the inverting input. These two are just to do with a comparator. Basically, you know what a comparator looks like. It literally doesn't have any feedback, which means the gain will be 100,000, and you just have two potential dividers. So depending on which one is higher, the output will saturate positive or negative. Simple as that. So usually that'd be 0 volts, that'd be like 10 volts for argument's sake. And then it will saturate positive or negative depending on which input is higher. Okay. This one would just be for a buffer. Believe it or not, there is such a thing as just feeding that round. That will give you a gain of 1. Okay, and the idea of doing that is because the output follows the input, but you have more current, or you can say the output impedance is lower compared to the input impedance, so you've got more current available by doing that. And then you've got two equations for slew rates. You know what that one looks like. Your input would go up like that, and quite often your output, if it's non-inverting, would kind of do that kind of shape, won't it? You could also do slew rate with a sine wave as well. Okay, so looks like quite a lot. Oh, the only thing they haven't given you on op amps is the GBP equals G times bandwidth. Yeah. And obviously you can also find it graphically, can't you? You know what that one is, 70%, yeah, dead easy, 70%. So that is basically what they can ask you with op amps and the equation. So I would say with op amps, you're going to look at your data sheet quite a bit. You can see there is only one equation in signal conversion. That's a bit boring, isn't it? Why is that the case? I'm sure you're going to say yes, because it's core concepts, isn't it? Of course it is. If you've got an ADC going off down here, you know what's going to happen. You're looking at a potential divider equation to find the voltages, V1, V2, etc. That's what you're looking at. You can have your op amps going off there. Oh, going off there. If you have generally, if you have had an extra op amp, it's called an overflow. Which would connect over there. I'm not going to build the rest of it for you. There might be a bit of logic involved because they might ask you to work out the logic here for the priority encoder for these bits. But again, just follow the usual thing, use a Carnot map if needed, all those sorts of things. And a DAC, again, it's just using, it's a 3-bit DAC, it will have 3 inputs. You work out the least significant bit, then you half, half, and half. So if that's A, B, and C, A equals LSB, least significant bit, work out and half for B and half for C. It's that easy. And it's just your bog standard equations from the previous page, just inverting op amp equations there. The resolution is the smallest voltage step. So in this case, the resolution would be V1, the input voltage range, over 2 to the n. So let's say it's 4 volts, and these are all 1k each. Then the resolution would be 4 over 2 to the power 2. So 4 over 4 would be 1. And I can just look at that and say, I know there's 1 volt there. And you guys can look at that by ratio and say it's 1 volt as well. I'm sure you could. Okay, that's pretty much ADCs, DACs. They could also ask you, this is called a flash converter, this one. They could also ask you, why would you use the SAR? Well, you'd use an SAR when time is not an issue or speed is not an issue. Things like measuring the temperature of a greenhouse, you don't need it to convert straight away. But if you're measuring something like audio, which needs to change rapidly, then you'd need to use a flash converter. These equations relate to AC and passive filters. So the reactance, which is the same as resistance really, reactance of a capacitor is 2 pi FC. The reactance of an inductor is 2 pi FL. Remember, if you put a capacitor and an inductor in parallel, you create something called a resonant filter. Okay, so what will happen is the current will go down go through the capacitor, or it will go through the inductor depending on the frequency. And if you get the reactances equal to each other, do a bit of rearranging, you can get this equation here. It's called the resonant frequency. Okay. From that, we can work out something called a dynamic resistance, which is like the equivalent resistance of the LC network. And then obviously you can work out the quality of it. Q factor is unitless. Usually about 100 is a good Q factor, number of 100. This one over here is called impedance. So if you have a circuit which has, so let's get a pen out. So if you have something like this, which is you can tell me, is it high pass or low pass? Well, low frequencies are going to get through, aren't they? High ones won't, so this was a low pass filter. But if you wanted to work out the overall resistance of this circuit, you use this equation here. So, so you'd say V out, slight potential divider, equals V in, multiplied by, normally be R2 over R1 plus R2, where R2 is the bottom resist, is XC, over R1 plus R2, which is actually Z, because all of that there is the overall resistance. It's called impedance. Well, that's the overall impedance. So it's a triangle, isn't it? It's 90 degrees phase difference. What else can I say about this? Capacitances are usually small. So if you've got something that says something like 100 nanofarad, and you're working it out, make sure you put 100 times 10 to the minus 9. Yeah? Okay. Other than that, I think those equations speak for themselves, but they're easy equations to use. So what I'd recommend doing is maybe go to a component one paper, or you could even go, if you want old spec, they're in ET4, and maybe try a question or two with those, because they are easy. Communication systems, these bottom two equations come up in optical comms as well. But yeah, you can work out the bandwidth or the number of channels if you know the available bandwidth and the channel bandwidth. Sometimes it might come out as an odd number, like, I don't know, 65.3. Therefore, you'd round it down, so it'll be however many channels I just said, whole channels. Okay, so channel available bandwidth that you've got and the channel bandwidth, one divided by the other. Data rate is measured in bits per second. Bandwidth is obviously measured in hertz, so that's where the 2 comes in. So to convert between the two, if we divide by the 2, then you can get available bandwidth by doing data rate over 2. Yeah. This one, we did do some work on this about how to rearrange it. Do you want me to just do it? I'll just do one. Why not? Why not just do one quickly? Get my pen. So if we want to make, for example, P in the subject, now I think I might actually put some values in, shall I? No, I won't, I'll just do it. So basically, we take 1/10 of the value, so it's going to be, to rearrange this, it's going to be G in decibels over 10. It's going to equal log to base 10 P out over P in. Yeah, and then to get rid of a log, we take 10 to the power of that value. So it's 10 to the power of gain in decibels over 10. That's got to equal P out over P in. Then you can multiply both sides by P in to get P out. Yeah, so that's how you rearrange that one. Okay, looks scary, but it's not too bad. And the bottom one to do is signal and noise. PS is the power of the signal, and PN is the power of the noise. Okay, so hopefully that makes sense. You can do it with voltage as well. Voltage of the signal, voltage of the noise. Okay. Okay, so wireless comms is AM and FM. This belongs to AM. Other things belong to AM as well, but essentially, you know what an AM wave looks like. It's the one that does that. Yeah, when there's your carrier. So you've got the carrier signal is a high frequency, and then the audio signal is a lower one. Modulation or depth of modulation is this equation here. But remember, we do it, or we can do it, by finding the midpoint there and the midpoint there. And then if you measure from there to the midpoint, label it as A, and from the midpoint to that peak, midpoint to that peak, and label that as B. You could also work it out by doing B over A times 100. It's the same equation, really. But you can work out the depth of modulation that way. Other things they can ask you is to work out the time period. So obviously, from there to there will be the time period of the carrier. So T carrier. So, sorry, not the carrier, my fault. The time period of the signal, like the audio signal that you want. Yeah. And then how many pulses happen in that time will be the time period of the carrier. So if there's 1, 2, 3, 4, 5 happen in that time. So the time period of the carrier would be obviously a fifth of whatever the time period of the signal would be. Yeah, because 5 of them happen in that time. So make sure you count. In fact, I'll probably count 10 cycles. But yeah, because I count how many cycles happen. These next ones, well, these next two, should I say, FM, frequency modulation. Okay, so beta is again the modulation index. The carrier frequency, they try and trick you sometimes. They sometimes say a carrier which is, I don't know, 2 gigahertz has been modulated by a carrier frequency of 15 K. That's what you're using. It's the delta, it's the change in the carrier frequency. It's not the carrier frequency itself. And bandwidth we can work out, obviously, quite easily. This is just kind of its separate thing, but it's wave speed, isn't it? Speed of light equals the frequency multiplied by the wavelength. Okay, that might crop up. Okay, so this is a difference amp, so it's quite easy. One with the 4 resistors. Yeah, you've got it. I think you need that one. Look at that. I'm a really bad drawing. That one there. One goes to 0. And then one loops round. Okay, so basically it's V diff times gain equals V out. You might have a potential divider on here. They sometimes do it as a little diamond shape, don't they, like that, with the components. And then they connect one to the other. So that's that one there. They can ask you about grey code, CBA. So it's one where it starts with 1 0, 2 1s, 2 zeros, 2 1s, 2 zeros. B starts with 2 zeros, 4 1s, 4 zeros. C starts with 4 zeros, 8 1s, 8 zeros, etc. So that's grey code. Okay, and sometimes they ask you about revs per minute and things like that with slotted discs. So sometimes they might give you like a slotted disc type thing like that. And say it's got 100 slots, it turns around 10 revs per minute, how many slots are counted. So you just need to logically work out what's going on. So turn it into seconds and things like that, revs per second, or it might say how many counted in a second or whatever. Yeah. So hopefully that's straightforward. So you're just using a bit of physics there in that one actually. The slotted ones. Grey code, they can ask you to colour in a coloured disc, coded disc. What's the advantage of grey code? You only have one change per logic level. And then instrumentation, they can ask you various things. They could give you a strain gauge and a dummy strain gauge, ask you to find the output voltages. But it's simple stuff. It's potential dividers again. It's core concepts actually. Yeah, potential dividers. Okay. Timing circuits. So we obviously have time constant R times C. That's how long it takes an RC network to charge to 63%. How long does it take to charge to half the supply? 50% is 0.69 RC. You don't get that on the data sheet, but you might want to use that one. So 0.69 RC is the 50%. R times C is going to be longer, obviously, because you haven't got the 0.69 in there. Yeah, it charges to 63%. Right, the one with the 1 minus in is a charging type one. So this is how to find the voltage across the capacitor if it's charging. Worth pointing out that if it's charging, the RC network will be in series. If it's discharging, the RC network will be in parallel. Series for charging, parallel for discharging. The one with the 1 minus in is charging. The one without the 1 minus in is discharging. The ln or natural log is on your data sheet. Sorry, on your calculator. And similarly with the E, the exponential button. Okay, so charging, discharging, charging, discharging. This is for a Schmidt A-stable, so the frequency can be found 1 over RC, Schmidt A-stable. Okay, we all know that frequency is 1 over time period. I don't even know why they give you that one, because it's similar to Ohm's law. It's just something that should be ingrained in your brain. This next one is to do with monostables. So 555 monostable. Okay, so it's 1.1 times RC. The next ones are to do with the 555 A-stable. So mark time is called the high time. The space time is called the low time. If you put the two together and do 1 over it, you get this equation here. Luckily, you don't have to work that one out. So you can work out the frequency. And then this is doing mark to space ratio. So if you want to do the mark to space, the on time over the off time, it's both the resistors over just the bottom resistor there. So that's how you can find the mark to space ratio. I'm not actually going to draw anything on this one because there's a lot of equations on there, but it's worth mentioning. Again, capacitors will probably be in micro, times 10 to the minus 6. Make sure you do that. I see so many students with, let's say, two 10k resistors and a 300 microfarad, and literally just put 10 plus 10 plus 300. I'm sorry to say it, but think about it. It's killer, and it's micro. Yeah. Go back to the data sheet. You've got prefixes on there. Put them in. Yeah. This one, the modern calculators will do that in one go. In the olden days, you'd have to do that in little stages, but the modern calculators, you can literally just plug that in and press equals and get the right answer now. So it's quite nice. Okay. Sequential logic. Definitely the first question of paper 2 is sequential logic, isn't it? But there's no equations. No. Okay. So what are you using? You're just going to be using logic systems. So basically, do you know what truth tables look like and all that sort of stuff? Then there's a lot of D-type flip-flops, up counters, down counters. Yeah, I'm not going to go over that again. You should know those by now. And there might be a bit of timing diagrams as well going on there. Yeah. So a bit of timing diagrams going there. Remember how a D-type flip-flop works. Q copies D on the rising edge of the clock. SR flip-flops are kind of there as well. But sequential logic, it's hopefully straightforward there. Remember when if you're doing a sequential counter, you have the output and then you have the next output. Remember, you fill it out when it goes diagonally up or diagonally down, where you fill it out. Probably, why don't you try question 1 and question 2 of a component 2 paper at this moment in time. So pause me and see how you go with it. Okay, so digital comms, no equations there, but it's all your things like, your pulse amplitude modulation, your pulse position modulation, your pulse width modulation. So it's to do with that. So if you remember that one where you'd have, your samples would be there, and there. And then obviously if it's amplitude, you're changing the height of the thing. If it's position, you're going to the left or to the right. And if it's width, you're changing the actual physical width of the thing. So maybe look at digital comms component 2. And then the other thing is you need to know the PCM transmitter and receiver. Yeah, so if you remember what, I'm not going to draw every what's inside of them, but it should look something like that. That's the thing that goes out there. Yeah, where you've got the clock, the piezo clock. Remember, the piezo clock has to be n bits faster than the sample clock. Yeah, there's your sample clock. Yeah, piezo clock there. Yeah, remember that one? And then you get a bit stream. There'll be ones and zeros like that. Yeah, coming along. And then obviously to regenerate the signal at the other end, you might have noise and distortion. Do you remember that? To regenerate it. So obviously you can use your Schmidt trigger going on there. And then obviously it might look something like that. Look it up yourself. I'm not going to bother putting all those things in. Schmidt triggers, you get asymmetric and symmetric. But remember, the resistors, even though I told you complete opposite all for the last 2 years, you can them the opposite way round. So you have positive feedback going there. If you don't have negative feedback, the gain will be 100,000. So the output will saturate positive or negative. If that's V in and that's 0 volts, this one particular one here would be a non-inverting. And then how to work the resistors out. Remember, you just draw them out like that. We know we've got 0 volts in the middle. That will be positive or negative voltage. And then we'd work that one out just by doing, voltages across there, voltages across there. It's basic potential dividers or ratios, isn't it? If they're the other way round, if they were the other way round, you'd have 0 volts on the left-hand side, and again you'd just use potential dividers. If you have a power supply there, so let's say it was 2 volts for argument's sake, then you'd actually have to have 2 volts at that point. So it becomes slightly different because you have to work out the positive and the negative. You have to work this out to be positive saturation and negative saturation, with the voltages going the other way. So it'd be slightly more tricky. It's called an asymmetric one there. Okay. But hopefully that makes sense. And remember, if you're plotting this one here, V out against V in, if it's non-inverting, the lip's coming from the non-inverting side. So this is still a non-inverting version. Okay. Okay, so optical comms, these two equations come back in again. The other thing that comes back in is basically a lot of words, isn't it? It's knowing what dispersion means, for example. It's talking about attenuation as well. So you get causes of attenuation. So the signal, the light degrades over distance. So you talk about what happens there. So look up in the notes again. We've done a lesson on that, on the attenuation and on the dispersion of the optical fibre. You need to know what's inside the optical fibre, the core, the cladding, the jacket as well. And there is a circuit, or a couple of circuits, but it's basically transistors. Let me just get the pen out. See the transistors, bog standard, where you'll have some sort of transistor there, and then some sort of photo transistor or photodiode on this side here, and it'll just be using circuit rules. Or I've seen op-amp detectors with similar type things where you'd have a resistor there and then some sort of photodiode thing going off there. Photodiode going off there. Yeah, and again, if you know the voltage, you can just use circuit rules again to find. If you know the current, you know the voltage, the same current will be going through that way. And then you can work out the resistor value or whatever it might be. So there are a couple of circuits called an op-amp detector, that one. Okay, and this top one will just be a photodiode circuit. But yeah, I'd probably just, in terms of the data sheet, it's just those two equations, or a bit of circuit rules if you've got to draw one of those. Okay, power supplies, mains power supplies. These first two are for working out the peak. So what basically happens when we get our electricity from the grid, we get the rough AC signal like that. It goes up to about 339 volts actually, down to about minus 339. But if you're to take the average value of that's called the RMS value, and it's about 70%, funnily enough, it's always 70%, isn't it? That voltage there would be about 230 volts, between 230 and 240 in the UK. Fluctuates at different times of the day, but that's the RMS, the root mean squared voltage. Okay. When you get to year 2 power supplies, they could ask you this question here. They could ask you to work out the output voltage across the load. I think we prefer to just use I prefer to use potential dividers, but if you remember, if you had your Zener diode there, you'd have your op amp there, wouldn't you? You'd have your emitter follower there, then you'd have a potential divider there, wouldn't you? So that's what's going on. Let's just leave that one mounted there. Basically, then it would always say what is V out. Well, VL, the voltage across the load, that's that bit there. So if you know the voltage across the Zener, you can work it out because the feedback resistor is that one, and R1 is that one. I prefer to just use potential dividers. Let's say the voltage across the Zener is 10 volts. Just use ratios. If it's 10 volts across here, you can work out the voltage across that one by ratio. But it's horses for courses, isn't it? This one's about ripple voltage. So half wave rectifier. If you've got your thing like that, there's a half wave rectifier. It might go up and down like that, up and then down like that. Then this bit's the ripple, the voltage across the ripple. So you can work that. That's current, by the way. Where's that? Where's my pen gone? That bit there is current, not one. It's current. Frequency of the ripple would be 50 hertz, or if it's full wave, it would be 100 hertz because you have twice as many ripples. Okay. Apologies about those noises going off. It's annoying me too. In terms of the data sheet and high power switching, there's only that one equation, isn't there? So it's the one where obviously if you had a, that sort of job going on, and you asked to work out the, see if I can draw that. You asked to work out the phase angle. So it might look something like that, mightn't it? So quite often it might ask you to work out the phase angle. Yeah, and then it obviously can ask you about, the voltage across the triac against the voltage across the load, and it can ask you to plot the two. Remember, it's those weird shaped graphs. So I'd recommend having a look at those. But and then obviously if it's just using the thyristor, it will be usually a graph, and it's just using circuit rules. When a thyristor is on, you need to say what the voltage is. When you unlatch it by using capacitor commutation, it drops down by whatever it is, whatever the power supply is, drops down by the same amount as when you press the switch. So it's just using circuit rules and voltage arrows and maybe filling out a table or something like that. But this one hopefully straightforward with the actual graph there. So I'm just show you the graph very quickly. So you probably have something. This is my original signal. That's my original signal. You'd have the voltage across the, let me just do the voltage across the this one, VC. So VC would be out of phase. You know that one, don't you? I'll label that one VC. This one's obviously the supply, VS. And then obviously we know if that's the firing voltage and that's the negative firing voltage. We know when we go past the firing voltage, the thingy turns on. I'll turn that off. So it looks something like that, down, round, and then up to the negative firing voltage, and then like that. So that'll be the voltage across the thyristor, and then the voltage across the load. would be the other bit of it. So stop there, be that bit, and then go round to there. You can see the idea that basically this bit is that bit there, that bit there, and then this bit is that bit there. So they kind of add up essentially. Okay, so it looks like a shark. Think of the voltage across the thymus being the shark bit, the voltage across the load being the other bit, or shark fin, should I say? Okay. Okay, just to finish then, audio. You've got your 4 filters, and you're going to be using that to find your break point. Remember what they look like. The capacitor could be in 4 different places. Try and remember what happens with the capacitor. Try and think about what it does. Capacitor, low frequencies can't get through. High frequencies can get through. So resistance or reactance drops. That's high frequencies. Yeah. Okay, so you've got your 4 filters, and they can ask you to plot it log scale. Hopefully you're okay with plotting that. These equations are just basically to show you if you've got an emitter follower power amp, you have to take 0.7 off. Bog standard emitter follower, you'd have your speaker, something like that. Really badly drawn speaker. There's my speaker. So the idea is V out is 0.7 volts less than V in. Yeah, there's V in. Do the same with the MOSFET, but obviously take 3 volts off from MOSFET. And then this one is power amp. It only works for the push-pull. Remember the push-pull? See if you guys can draw the push-pull using MOSFETs. Make sure you put the arrows on as well. So I'm going to do the easier one using transistors here to show you it. Yeah, this one will have crossover distortion. So to remove crossover distortion, we put an op amp like that, an emitter follower, also a voltage follower op amp. There's the speaker. Positive, negative. So no crossover distortion. And then obviously you can work out the power by doing V squared over 8RL. Okay, so that's taken us to the end of the data sheet. The only thing I've not mentioned on the data sheet is the pick stuff, but I hope that's straightforward. It's just looking it up, isn't it? Looking what the commands are. If you would like me to go over anything with the pick stuff, maybe just message me. I can always do another video.